طيب بسم الله الرحمن الرحيم. Today inshallah we're going to start a new part. We're going to start a new part in the course. So part 2 in the textbook, which covers the standards, and basically we will try to cover three major standards. The first one is the Wi-Fi, and in each of these standards we'll try to discuss mainly how to provide service differentiation and quality of service within this environment, within this wireless technology. Okay. So the first set of standards is wireless local area networks, or Wi-Fi in short. This actually includes all the 802.11 family of standards. Okay. There are multiple standards that are included in 802.11, and in the first half of this part, we will try to get familiar with the standard itself, and then in the second part, we will talk about what are the techniques and what are the aspects in this standard which facilitates service differentiation and quality of service. Okay, so from the name, of course, you know why what LAN is all about, right? So local area network, it covers a small geographical location, okay, using wireless technologies. So basically there are two parts. As I said, we have 802.11, which is the base standard. Actually, this includes multiple variations of this standard, so we need to get familiar with some of the characteristics of the different variations of this standard. And in the second part, we'll talk about the QoS extension to this, which is what we refer to as 802.11e. Okay. All right. So this graph here shows the global picture of all the 802 standard family. Okay. So in 455, we've covered 802.3, which is Ethernet, and a little bit of 802.11, very superficially, in network 1 and network 2. And in this course as well, we're going to cover 802.11, and we'll try to cover also 802.16 and 802.15, which is Bluetooth and Zigbee. These boxes here, they refer to medium access control and physical layer part of the standard. There is the logical link control, which is 802.2. So why do we have this shared here? Does anyone remember why we have the logical link control is shared between all these standards? It's a 455 question. Okay, so people who studied 455 with me, they have more pressure now to answer this question, because we discussed that you're not away from them. Yes. You should know the answer, okay? Because the nature of the logical link control sublayer, okay, is medium independent. Logical link control acts as an interface between the network layer and the data link layer and physical layer, okay? And in that, it supports only error detection and correction and framing. So the nature of this sublayer, okay, is very agnostic to the type of medium that we're talking about. Whether it's wired or wireless or anything, it does not matter for this logical link control sublayer. And that's why the standard itself, it's common. It's common between all these medium dependent kind of layers. Okay, so these boxes are heavily dependent on the type of medium that we're talking about. Not just the type of medium, because 802.11 and 802.16 and 15, they are all, focusing on wireless. Okay, but each one of them covers a certain aspect of the wireless technology. There is one for short range, one for long range, and so on and so forth. So they are heavily dependent on the type of medium that we're talking about. All right. So So for wireless, as we said, wireless is the most challenging in terms of facilitating robust communication and also in providing quality of service due to the dynamic nature of the wireless channel that makes the support for quality of service highly challenging. Okay, so the wireless media have no clear physical boundary. So we don't have like a wire which has beginning and end. In wireless, the boundary is fuzzy. Is not like there's no one line boundary that we say that after this line there is no range or there is no coverage for wireless signal. So one of the challenges is that wireless has no physical boundary. So we don't know exactly where the coverage of the wireless signal ends. Sometimes it ends at the end of this room, and sometimes it can, penetrate and go further, depending on the transmission power that we use, depending on the type of frequency that we use, and depend on so many things. The other thing is the coexistence of multiple LANs together, and co-location or coexistence of multiple LANs that overlap together makes the coverage even more challenging because some of the users, they will be covered by two different access points or two different LANs, in which case we have to associate these users to a particular access point, and we have to take into consideration multiple factors. So actually quality of service could be one of the factors to associate certain users to certain access points versus the other, because this user might be actually covered by 2 or 3 or 4 different LANs. In fact, the same issue exists even with different wireless technologies. So one user could have Bluetooth coverage and 4G and 3G coverage in addition to Wi-Fi or Wi-Fi direct. So this user has ultimate flexibility in terms of what wireless technology he or she can use. And one of the issues is that which technology I should use to facilitate the actual quality of service that I expect for a certain application. Sometimes one wireless technology can do the job, so I can just connect to Wi-Fi and that's it. Or maybe the capacity of the Wi-Fi will not be enough for me, so maybe I can concurrently connect to 2 different wireless networks, and maybe one of them is Wi-Fi and the other one is 3G or 4G. Cost also is another factor, because if I connect through 4G, I have to pay money. So if I'm in the range of multiple, wireless technology or wireless access points, then I have to select which one to connect to, maybe 2, maybe 3, so it depends. Radio interferences with external devices. And this is not just another wireless node that happens to be in the range. This actually includes other types of devices, even microwave at home interferes with the wireless signal. Okay? Any external device might actually introduce some kind of interference to the wireless signal. Even lightning, any like rain or anything, any weather condition might actually cause some interference to the wireless signal. And in that case, it's very interesting to try to maintain a sustainable and robust wireless communication in different environments. Whether this environment is packed with different external devices that interferes, or weather condition, with other mobile nodes that happen to be in the area while you are communicating wirelessly. So all these factors, they affect the wireless signal. Mobility as well, whether you are on a car that drives 200 kilometers per hour, or you are on a bike that goes like 1 or 2 kilometers per hour, it does make a difference. So mobility affects the quality of the wireless signal that you can have. Not only that, when you are actually mobile, you move from the coverage of one access point to another. So how do you actually hand off, or how you transition your communication from one access point to another? Okay, how frequent can you do that, and does that affect the communication that you're currently having? So if you happen to talk over the phone and you are moving very fast, so this means that you have to hand off, or you have to switch your connection from one access point to another, or from one base station to another, if we're talking about cellular network. So if you go very fast, you have to do this, switching very, very often, very frequently, and there is a limitation for how much time you can spend on this switching, which affects your the quality of the communication that you're currently having. Okay. Feel free to stop me whenever you have any questions. So power limitation as well, because we're talking about mobile phones or mobile wireless nodes. So this dictates the fact that most of these wireless nodes, they are battery operated. So the fact that they are battery operated makes any type of computation or any type of communication that you do very critical, because if you don't do that efficiently, then you drain the battery very fast, which means that after some time, you don't have any power or any energy to sustain the communication, and you have some disruption, service disruption, and so on and so forth. So it's very important for wireless mobile devices that we provide quality of service based on the expectation of the user exactly. So over-provisioning will not be very good in that case, because over-provisioning means that you give more resources to the user, and the user has to utilize more resources, in which case, for example, his battery will drain fast. So that's not advisable. So it's very good that I maintain the quality of service based on the user needs exactly, not more and not less. Because less will give me degradation in quality, and more will give me degradation in the battery, or the capacity of the battery that I'm using. So all these factors play a very important role in designing any standards or any quality of service techniques, especially for wireless technologies. Okay? And that's why even nowadays we started to talk about renewable energy for wireless devices. So we need these wireless devices to extend their energy capacity by maybe harvesting energy from the environment, from other wireless signals, because even wireless signal has some energy. So I can harvest energy from a wireless signal, I can harvest energy from a solar cell, I can harvest energy from anything. Okay? So with that, the baseline 802.11 standard was actually released or approved in 1997. Okay? Since then, we had about maybe 10 or 12 different variations of these standards that work just as efficient, but with more features or more capacity or different characteristics that fits a specific environment. So we'll talk about that a little bit. As we said before, the 802.11 family, it covers the MAC layer, or the MAC sublayer, and MAC, we know that MAC is part of the data link layer, okay, and the physical layer, right? The baseline standards, it supports a data rate of around 1 or 2 megabits per second, all the way up to 11 megabits per second. So the base 802.11b, it supports up to 11 megabits per second. And this is actually over 2.4 gigahertz. What does that frequency mean? This means that this is the carrier frequency around which these standards actually work. Okay? Because as we know, for wireless technologies, the signals, when we digitize these signals and deal with them in the digital domain, we call the signal a baseband, or it's in the low frequency. But once we start to communicate wirelessly, we have to select a certain frequency range that we use for communication, right? And this frequency is very important because Like for example, if we send it over like 900 megahertz or something, we will interfere with certain communication that happens to communicate in this range. So 2.4 gigahertz is one of the very attractive frequency or carrier frequency that attracts many wireless devices. And the reason for this is that it's license free. You don't have to pay money to manufacture wireless devices that work in this range. So they call it ISM band. So this 2.4 gigahertz attracts many standards actually. So even Bluetooth works in that range. Many of the cellular technologies, they use that 2.4 gigahertz. So the advantage is that it's free. You don't have to pay license to use it. But on the other side, of course, if everybody's using it, then this will affect interference. So inter-technology interference and these kind of things, they play a very important role in this band specifically. And that's why one of the variations of this standard, which is what we call 802.11a, it actually opted to use another frequency range, which is 5 gigahertz. Okay, so 802.11b, 802.11g, they work in 2.4. Okay, 802.11a, it works in 5 gigahertz. So in 5 gigahertz, the good thing with that is that 5 gigahertz, you have less interference from other nodes. However, one important fact you need to know, the higher the frequency is, the less the range. Bravo عليك. Yes. So the range of the wireless signal that's covered by the wireless signal drops drastically when you increase the frequency. Okay, so you can find that the range for 802.11b and g is maybe around 25, 20, 30 meters, something like that, depending on the type of environment and the obstacles that you have and so on and so forth. So if you shift it to 5 gigahertz, you drop at least to half. Okay? If you want to maintain the same range, what do you do? If you want to maintain the same range using in the 5 gigahertz, what do you do? What do you need to do? Multiply. Increase a range is dictated by the range of the wireless signal is dictated by what? The transmission energy or the transmission power that you use, right? So if you work in high frequency, the range will drop, right? So you increase the transmission energy, but this means that you will spend more energy. It's up to you. So we switched to 5 gigahertz to reduce the interference. We got another issue with the range. We can increase the transmission power to maintain the same range, which means that we need to spend more power. So that's why one of the technologies in the physical layer that allows the node to reduce interference, even in the 2.4 gigahertz range, is what we call frequency hopping spectrum. So as we will see later, that around 2.4 gigahertz, Wi-Fi usually maintains around 11 channels, or maybe up to 128 channels or something like this. We'll talk about this later. So around 2.4 gigahertz, we have small channels, small like sub-channels, all of them around the 2.4 gigahertz, right? And the idea is that if you want to maintain communication between some nodes and the access point, you use one of these channels. So at home, if you actually play around with your router configuration, you will find one of the parameters is actually the channel number. So you can set this channel number manually, or you can leave it auto. What happens is that if you leave it auto, the router will perform some measurements and will find which channel that it can best use at any point in time. Okay. Using frequency hopping spread spectrum, the access point with the agreement of the nodes can actually hop from one channel to another automatically to kind of maintain the interference within a certain range. Because some channels, they happen to have more interference than the others, right? So you can actually switch the frequency from one channel to another, which is what we call hopping. So we hop from one frequency to another, and this happens very fast. That's why it's called frequency hopping. And the frequency hopping is used to reduce or to mitigate interference, especially when you have multiple wireless LANs in certain area, so they overlap together. So if you use the same channel here and here, okay, chances are you will interfere. So what will happen is that we will change the channel here and change the channel here randomly, so that they don't collide with each other. So you don't have any overlap in terms of frequency, and you change this frequency from time to time, or change the channel from time to time. And the reason is that in each channel you get certain level of interference. So if you switch amongst them all, this means that the level of interference is like kind of balanced between all the co-located cells or the co-located wireless LANs. Okay. So as we said, the 802.11b, it works up to 11 megabits per second at 2.4. 802.11g tries to increase the rate. And it tries to increase the rate by using different technology in the physical layer. So higher modulation, things like that. We're not going to cover this. But it can get to 54 megabits per second in the same frequency range. And as we said, 802.11a tries to solve the interference in another way by shifting the frequency from 2.4 all the way to 5 gigahertz. Okay? So all these standards, they cover data very well, but they don't cover multimedia as efficient. Why? Because for multimedia, we know we need what? We need quality of service. We need service differentiation, right? So these standards, they don't provide that service differentiation, right? So that's why the all of them, except for 802.11e, which provides signaling for providing this quality of service through service differentiation. Okay, so this is the standard that we will spend more time on as part of this course. Okay, any questions? All right, so the 802.11 architecture defines what we call the basic service set and extended service set. The basic service set is basically an access point, or even the access point is optional in that case, and a set of nodes. Okay, so this is a basic service set, which means that all these nodes, they communicate through the access point. Okay, and the extended service set. If the basic service set works without the access point, we call it a ad hoc. We call it ad hoc, which means that the communication does not necessarily have to go through the access point, right? And in many cases, we can understand this logically by the fact that, you know, if I'm communicating to a person close to me, okay, and the access point is very far from both of us, it's not efficient that this communication has to happen through the access point, in which case he has sent to the access point sends to me. Okay, so instead of sending this through two types of communications, we can just send to each other directly, right? So that's logically understandable. However, ad hoc communication introduces extra challenges, because if you don't have a centralized control for communication, it makes things very ad hoc, and we always refer to the fact that ad hoc means that it's random, it's uncontrollable, right? And that's the nature of the ad hoc communication, is that it's uncontrollable. You don't have control. So you can communicate to one next to you, but you will affect the communication of two other people who are communicating together. And there is no, like centralized controller that has any control over this communication, because the access point organizes who will have access to the medium at any point in time, right? When we talked about medium access control, okay, if we imagine that we are in a meeting and there is one moderator, right? This moderator will control the meeting. He or she will give access to a certain node to communicate at a certain point in time. But always ad hoc refers to the fact that it's ad hoc, it's random, so we don't have any control. So when I communicate to one next to me without the engagement of the access point, we might actually collide with another communication that happens a few meters from us, and we don't know, and he doesn't know. Okay, because there is no one that overlooks all this communication together, right? So ad hoc is really challenging in terms of maintaining control to the medium.
Doctor, is the ad hoc network usually like it's like peer-to-peer? So it's
Right. This is peer-to-peer. Yeah.
usually
Right.
there is no access to the internet for that?
No, you could have access to the internet. One of these nodes may act as a gateway to the internet. Like if one of these nodes has access through 3G or 4G, this is in fact what we do if you have any wireless device that does not have access to the internet. What do? You can have your phone acts as an access point, okay? Using Wi-Fi direct. And this node can communicate with my cell phone, and then my cell phone will act as a gateway to the internet. So you can have one or two or three of these nodes to act as a gateway to the internet. So you could have access to the internet. But the problem is, within this ad hoc network, we don't have control. So we don't know how the medium is going to be used. So if you don't have control over how the medium is used, you might end up with a situation that the medium is used very inefficiently. So the bandwidth will go down. Okay? So ad hoc is really challenging. So the other alternative is what we call access point based, and we always refer to this as infrastructure mode. Okay? So this access point, in fact, is actually connected with an infrastructure. Okay? So there has to be an infrastructure behind this access point in order to facilitate the communication between one access point and another, or basically one basic service set and another. Right? In ad hoc, there's no such thing. So it's up to you. So you can form whatever topology you want. So for basic service set, basically the topology that we're talking about is what type of topology we're talking about here? Star topology. Okay? Star topology, which means that you have a centralized node and everybody is communicating with it. This is star topology. In ad hoc, you can have any type of irregular topology. You can have a square topology, you can have whatever you want, okay, depending on who communicates with who at any point in time. And because there is no control, the topology actually changes on the fly. So it makes the control really tricky, okay? So these are the two types. So you have the infrastructure mode and the infrastructure-less mode, okay, where you don't have any access points. So the basic service set is made of stationary or mobile wireless nodes or wireless stations, and a possible centralized station known to be called access point. And a basic service set without an access point is the standalone network or ad hoc network or infrastructureless network. So all these names refer to the same thing. Okay. And we have the extended service set. The extended service set here provides the communication amongst all the wireless LANs or amongst all the basic service set. So extended service set, in addition to the access point and in addition to the wireless nodes, we also have what we call a distribution system. This distribution system, it could be actually, in many cases, is wired. Okay? So this is a mix between wireless network and wired network. So here we could have switches, routers, and so on and so forth. And that's why we call it a infrastructure mode. Okay? Because we have to connect these access points with the infrastructure. This infrastructure could, in some cases, be ad hoc network. In which case, these access points use ad hoc communication. Okay, that's an interesting situation. So the distribution system itself is an ad hoc network.
So in this case,
and it could be using a different wireless technology. It doesn't have to be Wi-Fi. It could be 802.16 or whatever. Okay. Combined. It's a mix between wireless and wired. Yes.
not in the ad hoc mode, with the access points on ad hoc.
Okay, okay.
So the network it will be considered only wireless, right?
Yeah, pure wireless, yes, pure wireless. Yeah, but wireless has, we could actually have different wireless technologies. So we could have 802.11 here and 802.16 here. Okay, in which case the access points, these access points, they need to support both, which means that they need to have one transceiver for Wi-Fi and one transceiver for 802.16. Okay, so it becomes a little bit more complicated. But this is in fact what happens. Like even access points, they have wired network support. So we have Ethernet and we have Wi-Fi. Okay, so these access points, they need to have 2 or in some cases 3 different types of wireless communication or wired communication standards.
And a node can move between the PSS. If we have a node, it can move between all the PSS.
Yeah, absolutely, yes. This is what happens here in the university. So do you think the university has one access point and all of us are connected to it? It doesn't work. I mean, so you have hundreds of these access points everywhere. Okay, and you can configure these access points to have the same, they call it SSID, or this is the ID for the network. If this ID is common, this means that all these access points, they are part of the same global network. But each one of them is a BSS, okay? And all of them together, they are ESS, okay? And here there comes some interesting situation. Not only can you move from one location to another, you can actually be in a location where you are covered by 2 or maybe 3 access points. Okay, so which one do you connect to? Okay, so one factor is to connect to the one that has the strongest signal. So you have to do some measurements to see which one has the strongest signal and connect to it. Okay, or maybe if you can, do some signaling with these access points and ask these access points, will you be able to give me the quality of service I'm expecting or not? Because if not, I will connect to another one. Okay, so quality of service could be one of the factors based on which you associate to one access point versus the other.
But your quality of service is affected if the network is ad hoc or like.
Absolutely, yes.
Or wireless.
Yes, طبعا. Yeah. So as we said, I mean, the ad hoc networks, basically, they introduce more dynamics and more uncontrolled environment, in which case the quality of service will be more challenging in that case. This is not to say that there is no solution for this. There are many, many solutions for this. But that's why we need to see how we can do this. So.
In scenario where like now the mobile phones usually when they're connected to an AP and you have the 3G on, it would just flip between the two.
Right.
Does this happen because of the computation that you just mentioned? Like depending on the signal, if it's very strong, it would connect to it, else it would disconnect.
That's an algorithm. That's a very good question. This is an algorithm. So our mobile phones, they are configured with a very simple algorithm. If there is Wi-Fi, just connect to it. Don't think, because Wi-Fi is free. So they use the cost as the main factor. They don't look at quality of service. They don't look at energy consumption or battery efficiency. Or they don't look at these things. Although of course, I mean, in my group we have done a lot of research regarding this, and we can not only switch from one to another based on many factors. We can also connect to 2 or 3 or 4 wireless networks and send the traffic to the network based on the quality of service that we can get from this type of network. So this requires huge amount of optimization and communication and computation that you have to do in order to understand the situation really well and adapt to it. Okay? Any other questions? We don't want to lose anyone, so if you were not following, just let us know. Okay? So this overlap is what we call we have, so if you associate yourself to one access point, say this one, so the communication that happens in this other, BSS, for you is an interference, right? Because you want to communicate here, but you're also receiving another communication from here. And that's when we need frequency hopping. Something like frequency hopping can allow the communication in this BSS to happen, to use one channel, and this uses another channel. That's why when you set it to auto, you allow the network to select the best frequency for you based on the situation. So so the system will do some measurements, and based on that, it actually changes the frequency on each of these cells depending on the level of interference that you have. Okay? So this kind of overlap also introduces an interesting scenario. So this is what we refer to as colocation. So colocation is a very interesting situation where these access points may have some overlapping areas here. And within these areas, this is a type of interference that we can do something about it, because there is another type of interference that we cannot do something about it. Unless you want to change the location of your microwave and put it outside your house, or change the lighting. You can't. Okay, so there are some situations that you cannot just change the interference that's happening. But this is an interference situation which we can have some control. So and basically what happens is that these access points, they negotiate which channel to work on, and they hop between these frequencies so that the interference that each one gets is different, but on a long time horizon, it's the same, it's balanced. Okay? So if we know that one channel has interference more than the other, right? So I can use one channel and you can use the other, and then we can switch. So if we keep switching back and forth, back and forth, back and forth, over time, we are getting more or less balanced level of interference. But it's different. We're always different, in which case, we're not interfering with each other. Because there are two types of interference, as we said. There is an interference from the neighboring cells, or the neighboring access points, and there is interference from external wireless sources. Okay? So this interference from external wireless sources depends heavily on the frequency that you use. Okay? In some frequency, it's very high. In some frequency, it's very low. So if we keep this PSS to use the same frequency all the time, so this may not be fair to others. If the level of interference here is high and in other channels is low. But if we switch, then over time we are balanced in terms of the interference that each one can encounter at any point in time. Okay? Any questions? Okay. So this is how the channels looks like, but I think we can stop here and talk about this because it's a little bit complicated. So we'll talk about it next time, inshallah. Okay.